Hello and welcome everyone to this fourth session of this course on Bayesian Data Analysis with JASP. So now that we have clear the foundations of Bayesian inference and its extensions and applications, we're going to start to apply them to specific tests that we can be interested in. Okay, so now I will have a quick recap and then I will move forward to the most simple test. Okay, so as a quick recap, here is the Bayesian inference as obtaining posterior distributions using data likelihood and prior distributions and also the marginal data likelihoods. So these prior distributions need to be specified as a probability distribution with certain parameters. Then the data likelihood is going to appear retrieved from data as its name indicates, and then it's going to be combined into a posterior distribution which we can describe. The estimation of, for example, the highest density point can be done with some methods, for example, the MAP or the EAP. And for the simple test, we couldn't have analytical methods to create these posterior distributions. However, in complex models or more challenging models or situations, we will need to create these posterior distributions with simulation-based techniques. For example, the MCMC or Markov chain Monte Carlo methods that will create something like this, an empirically created posterior distribution that we need to assess is everything going correctly. For example, with the trace plots, with a caterpillar form, autocorrelations descending and without with very proximate values to zero, the shrink factor, or also called potential scale reduction factor, Gelman-Rubin statistic, or R-hat, below 1.1, and also the density curves of each chain get with realistic values. And with all of these tests, one thing that we need to check is that all of the chains have similar values. Okay. So now with all other diagnostics, for example, the expected sample size, the Monte Carlo standard error, or something like that, we can assess if the MCMC is doing a good job and if we can trust it. And if everything goes okay, then we can describe this posterior distribution, for example, with a point estimate, a mode, the credibility interval, or anything that we need. Okay, so in addition to this, we have the bias factors that it's a ratio of data likelihood that is multiplying the prior, and therefore we can use it as a some kind of p-value. And in fact, in certain situations, remember that they can hold very similar information to p-values, but they can have substantial differences. For example, the number of a bias factor means something different than a p-value, because p-values are built on the frequentist approach and bias factors are built on the Bayesian approach on probability, the expression of subjective belief on the occurrence of something. Okay. In addition, bias factors can also be interpreted as a continuum, and therefore you can use them as a degree of strength of support. More concretely, because if they are a factor and they are a quotient, you can see if they are high values, because it's from 0 to infinity. The higher the value and above 1, it's going to have some degree of evidence supporting H1. If the bias factor is 1, 0, you can make the inverse if you want. And also, if it is between 0 and 1, the support is going to be to H0. However, you can also have inconclusive evidence if it is between 3 and 1, between 0.33. More or less, these values are some consensus on this inconclusive evidence. Okay, so this is a main advantage towards p-values, because p-values cannot be interpreted as a continuum. That's why we have some thresholds like 0.05. However, with bias factor it's different, and we can use them as a degree of support towards some hypothesis. Okay, so now remember that thanks to the robustness of Bayesian inference towards multiple comparisons, we can use what is called the Bayesian update. And therefore, some very interesting analysis unlock, for example, the sequential analysis, that here is how a certain metric, for example, a bias factor or a point estimate or whatever, changes as we introduce observation by observation. And you can see here the general tendency to have stronger and stronger support, but we can also check for confounders or any other strange thing that is happening, and also for the robustness of our analysis. In addition, we can do this not within our data, but also between other data sets, for example, new data sets or different studies in the same project, meta-analysis, and also replication studies, okay? In addition, we have the robustness analysis that is more or less the same idea, however, of repeating the same analysis over and over again. However, instead of introducing new information, it's going to have the full data set, but we will start to change one parameter of the prior. Normally, the scale or variance parameter, because it's going to be the direct reflection of the informativeness of the parameter. I will elaborate a little bit upcoming, okay? So, as you can see here, you can plot the specific pattern of behavior that a bias factor or any other metric will have as we make this from super informative priors to super non-informative priors, and see the degree of change and the pattern of change. And for example, if most of it is from an interval from a very strong to strong support, you can conclude with some robustness that this is an okay analysis and the conclusion is reliable. However, if this is not the case, and for example, the degree of change is very high and shifts from very small support to extremely support or extreme support, therefore you need to be cautious with the conclusion, because it depends of the variance of the prior of that specific parameter of the prior that they need to change. The conclusions will change dramatically. Okay, so this is an example of a simple Bayesian test. It's a Bayesian t-test, and we have the prior posterior plot. Here is the prior, here is the posterior. As you can see here, there's a huge difference in posterior and also in variance, maybe because the data is pretty strong. And the sequential analysis reveals a general pattern towards stronger and stronger support, and the robustness analysis shows that more or less there is a strong support for H1. Now, the median of the posterior distribution is 0.22. With this is the credible interval, and we have a 3,100 bias factor, so it's pretty strong support for each one, and therefore we can conclude with a certain degree of robustness that in this case we can favor H1, that this parameter that is called delta is different from 0, more clearly between 0.13 and 0.3, and more or less 0.22. Okay, so a quick note on the priors. I have been talking about informative and non-informative priors because it's a very useful way of talking about them. I will just elaborate in a more specific note. There are two families of priors. One of them is informative, but also they are called subjective priors. They have a specific form that needs to be specified, normal distribution, beta, etc., and with expected load variances. Okay, each distribution will have its own way to specify this variance, but they need to be low because they are expressing a clear belief on the test. So this is like the informed or subjective Bayesian inference. We also have non-informative or default priors, and also called objective priors. Normally they have uniform distributions or specific forms like Cauchy or normal, but with very high variances. Okay, in some cases you can actually specify in the software to have an infinite variance, so for example 1000 as variance. This is done because they seek a maximum flexibility and to prioritize data likelihood. In many cases, they allow, because they are simpler, to have more specific analysis like sequential analysis or robustness analysis. A very well-known example of this is the Jeffreys prior. This is Jeffreys. And it was proposed actually to make replication studies more rigorous. So there is certain debate between these two families on which to use. There are more objective Bayesians and also more subjective Bayesians. The general rule is that as you have more previous evidence, you should be more informative, but this is not clear like 100%. Okay, so now moving on, now we will approach standard tests, but now from a Bayesian point of view. We will approach one sample t-test and then binomial and multinomial tests in this video. Then on forthcoming videos, we will have the Bayesian t-tests, independent and paired samples, Bayesian cross tables or contingency tables, and also Bayesian correlations. And finally, in the next video, we will approach the general linear model in the forms of ANOVAs and also linear regressions. Okay, so let's go with the one sample t-test, and remember that they have a free manual with all of the technical procedures in JASP to do these tests, okay? And also the data that I will use for the examples and also for the practical sessions is over there. Okay, so the Bayesian t-test needs, as you can imagine, to specify a certain value for the mean. It can be 0 or any value that you want, and then the software will automatically calculate a covariance D. This covariance D is the one that is going to be tested. So if you have a two-tailed contrast, you will have the covariance D to be 0 in the population, and if the respective one-tailed tests. You have certain assumptions. For example, you need a continuous variable. This is obvious. The observations need to be independent, and the mean needs to be a good descriptive. So you need to have a normal distribution or something like that, and don't have outliers to avoid bias, okay? So the prior distribution for this can be non-informative or informative. If you have a non-informative prior, the normal thing to do is to use a Cauchy distribution that has two parameters that are analogous as a median and standard deviation, but they are not exactly like that. So we have, instead of a mean, a location parameter and also a scale parameter instead of the standard distribution. So here is a graphical representation of the Cauchy distribution. So as you can see, they are pretty similar in form to a normal distribution, but they are not exactly the same from a mathematical point of view, and this is important. Okay, so the non-informative prior that JASP will use is with a location of 0 and a scale of 0.707, okay, as a default. This is changeable if you want, and start to become informative. Okay, if you want to an informative prior, you can change whatever you want, the location or the scale. Normally, to become informative, you need to have a scale. And this scale can be the degree you want. 1, 0.5, 0.01, or whatever. However, you can specify other families, for example, normal distributions with a specific mean and standard deviation, or students T distribution with the degrees of freedom, okay? And you need to specify all of those parameters. Whatever you choose, you will get a Bayes factor that can be 1, 0 or 0, 1, and in one-tailed test they are called plus 0, 0 plus if it's right-tailed, or minus 0 or 0 minus for left-tailed tests. You also will have a prior and posterior distribution plots. The posterior maximum with the credible interval, there's descriptive data like the mean, the criterion, some box plots or something like that with the credible interval also. And if you have a non-informative prior, you can opt to have a robustness and sequential analysis. Okay, so this is an example of the one sample t-test. Here is the example with using the Bayes factor 1, 0. As you can see here, we have 0.23, which is pretty weak. And if we turn it at 0, 1, the Bayes factor changes to 4, so more support for the null hypothesis in both cases. However, it's weak support, okay? So now we have the prior and posterior plot. Here is our prior and here is our posterior. As you can see here, they overlap in position pretty well. And the variance is kind of smaller in the posterior. This is a good thing. Here is the credible interval. We have the median and the credible interval here. These 2 points reflect the 0. And also we have the two types of Bayes factor and a pizza plot. Okay, so it seems that H0 has more support, but weak or small support compared to H1. So it's kind of an inconclusive test. Although you can conclude that there's some small support for H0. Then we have the point estimate here with the credible interval. Here's a ring-out plot that combines a box plot, a density curve of the data, and also the raw data, which I think is pretty neat. And also we have the robustness analysis and the sequential analysis. The robustness analysis shows that it depends kind of the scaled parameter of the prior, we will have different conclusions, because when we have our chosen prior, that is this one, we will have kind of support, some weak support for H0, and actually if we increase the scale of the prior and we make it more plain, more variant, more heterogeneous, the bias factor is going to shift towards more support for H0. However, if we make it more informative, it's going to become more and more inconclusive. In addition, the sequential analysis here is kind of different from the ones I previously shown you, because we have another thing, an extra thing in this simple test. We have our sequential analysis. As you can see here, it varies greatly. However, we have three types of lines. These three types of lines represent a combination between the robustness analysis and the sequential analysis. Now we can see three lines, because the black one is our specific prior. The gray one refers to a white prior, and the dotted line is a super white prior. Okay, so now we can see if there is a pattern of the tendency of our data supporting or not supporting anything in our sequential analysis, but how it can influence by the width of the prior. Okay, so as you can see here, the support could be kind of stronger in general if we choose an ultra-wide prior. However, we chose a different prior. Okay, so pretty simple, knowing what we know previously. Here's an example of one sample t-test when we have a one-tailed contrast. As you can see here, the prior and posterior are now truncated towards positive values, and the situation changes kind of a bit. And these are the two types of prior, +0 and 0+. Here are the two types of robustness analysis, that if we become left-tailed or 0+ or +0, then the output changes. It just flips down or up. And the sequential analysis is basically the same. Okay, so if we have problems with normality and the mean is no longer worthy of our trust, because, for example, we have huge deviations from normality, a floor or ceiling effects, a lot of outliers or skewness or something like that, we can opt for a non-parametric alternative from a Bayesian point of view. That is basically the Wilcoxon-Segnet rank test from a Bayesian point of view. Then we don't have an analytical method to estimate the posterior, so we need to estimate it through MCMC, and therefore we need some checks. For example, JASP will report the R-hat statistic, that is, remember, Gell-Mann-Rubin's ring factor P as F. It is the same. We have this criterion of 1.1. In this case, as you can see here, it's basically perfect or good. They have 1,000 iterations as default, and as you can see there, it is recommended that if the R-hat statistic is below 1.1, you need to double it and get to 2,000. And the rest of checks normally are trivial, because this is a very simple model. And it will give you a very similar thing, a prior and posterior, this one estimated through MCMC, the median with credible intervals, and also the descriptive data. However, in this non-parametric alternative, robustness and sequential analysis are not available, okay? Okay, so now let's go to binomial and multinomial tests. This is an example of a binomial test that instead of a mean, we will test a proportion. Now the test is going to be about the raw proportion, not an effect size like Commons D. We need to have a dichotomous variable with independent observations and also having a concrete proportion to test. Now the prior is different because we have a dichotomous variable, and then we need to think about the sampling distribution of a proportion. Therefore, if we choose a non-informative prior, we will have a beta distribution that has two parameters, alpha and beta. And the alpha and beta, if non-informatives, are going to be default. This is as 1, and it's going to create a very uniform distribution. If we want to become more informative, we can change any value of alpha and beta to then produce several forms. Okay, so as higher the two of them and the balance between each other, it's going to have a different shape. Okay, so the result is more or less the same. Bias factors, prior and posterior distributions, credible intervals with the maximum and descriptive data with the credible intervals and box plots, and also we have a non-informative prior, a sequential analysis, because the robustness analysis is not available. Okay, so here's an example. You can have the descriptive information with the proportions and the bias factors. Here is the bias factor 1, 0, and here is the 0, 1. As you can see here, in that are the dichotomous variable of participants having an iPhone or having another kind of smartphone. There is a little support to each of them. And if we make it at 0, 1, you can see here the same information, but it's clearer, because here having other, it's supporting, kind of supporting the, how do you say, it's kind of supporting the H0 because it's below 0.33. But if you just invert it, you just will get basically a 4. Okay, so here are the prior and posterior plots with the bias factor, the median of the sampling distribution, and the credibility interval, and the pizza plot, specifying as 0, but also here is specifying as 0.5. Okay, so the situations can change if you specify another criterion, which is obvious, right? Here we have some descriptive information with the proportions, the estimated proportions of the highest in the posterior with the credibility intervals from the two categories. And also here we have the sequential analysis, as you can see here, with a kind of pattern, because it increases a lot and then starts to go down in spikes. This is typical in this kind of analysis, okay? And robustness analysis is not provided because the alpha and beta parameters are complex in their behavior and in their interactions between each other. The form of the distribution can be very altered. So it would be a more complex structure. It's not simple, that you can create if you start programming in R, for example, because you can restrict one of the parameters, alpha, for example, and just start tweaking beta. Or the other way around, or just create a discrete set of alpha values and then tweak beta and see how beta changes in those 3 levels, for example. These kind of approaches are very common and you can use that with no problem. However, JASP has not implemented them because they don't know what do you want, so they prefer not to show. Okay, so this is an example of a one-tailed binomial test. Here you have the right-tailed, so the prior and the posterior are constructed towards positive values or values above the criterion, and here are below the criterion. As you can see here, this changes dramatically because when we have one of the categories having an iPhone with in this case with a right-tailed test, this curve is kind of intuitive. It is kind of truncated in one of the sides, but the other side is pretty clear. However, if we truncate it in the other side, then the posterior is going to become more and more likely towards the value and then will stop. Okay, so this is a very interesting thing to have in mind, that in Bayesian inference, if you have a very incompatible prior and data likelihood, the posterior is going to behave kind of strangely. If we have a one-tailed test, because the prior and the posterior will not be allowed to have certain values that need to have, because the data likelihood is pushing very heavily towards that direction, okay? So if you see this kind of thing, and you have, for example, a bias factor that says that just trust H0, if you want to be descriptive in that set, and you can encounter strange things. For example, this kind of credibility intervals just topping on the specific criterion, on the posterior doing strange shapes. So maybe you need to update and change your prior or your value, okay? Or just doing the other tail. Okay, now with the multinomial test, now we have a set of proportions that are going to be tested. So we need 3 or more values and independent observations. And we have non-informative priors that assume equal proportions in all of the values, and informative priors that specify a proportion from each value that you need to specify each and one of them. You will have bias factors, prior and posterior distributions, and the frequencies of proportions with the credibility intervals. So here's an example. Here is the 2 hypotheses with the bias factor. Here with non-informative prior, and here's with an informative prior. And also we have these plots that are basically the counts with the frequencies and or proportions, if you like it, with the credible intervals from each and one of our categories. So as you can see here, we don't have curves, our density curves, because it can be really complex, and they decided to go from this simpler approach. And remember that sequential analysis and robustness analysis is not available because we have a lot of proportions going on there. The prior can be very complex. Okay, so here are the really basic tests, but now with the prior and posterior technology of Bayesian inference. Okay, so in the next video, I will get towards bivariate tests.